Welcome to the Harper Classroom series of instructional videos. This video is on scheduling, Johnson's Rule, and Gantt Chart with Excel. The agenda for this video is first Johnson's Rule, a sequencing rule that generates a schedule to minimize the total processing time in the queuing system, where the queuing system is a queue or a waiting line to be processed on two servers in series. I'll first develop Johnson's Rule with a tutorial on the concept, and then how to solve a Johnson's Rule with Excel. Next is a Gantt chart, which is a time plot of a schedule. And the schedule in the Gantt chart will be a Johnson's Rule schedule. I'll first develop the tutorial on the concept applied to a Johnson's Rule schedule, but in that tutorial and the concept I will also pull out some diagnostics useful to analyze schedules from a Gantt chart, and then how to solve a Gantt chart with Excel. Look at Johnson's Rule, a sequencing rule that generates a schedule to minimize the total processing time in the queuing system of a single queue and two servers in series. So we start with a queuing system where we have a queue and two servers, and since we have two servers, we have two sets of processing times, one for each job. And the rule is, once we create our schedule, each job has to go through server 1, then server 2, then leaves the system. Johnson's Rule is an algorithm, and each iteration is made up of 3 steps, and the result is a schedule from the first position to the last position, and that schedule will minimize the total processing time. So let's start with step 1. Find the minimum processing time. The processing time is all 8 times of all 4 jobs, and the minimum time is 1. Step 2. Since the minimum time is on the last server, then schedule the job in the last available position. Step 3. Eliminate the job and go to step 1. Step 1 is find the minimum processing time of the 6 remaining times of the 3 remaining jobs. The minimum time is 2. Step 2. Since the minimum time is on the first server, schedule the job in the first available position. Step 3. Eliminate the job and go to step 1. Find the minimum processing time of the 4 remaining times and the 2 remaining jobs. The minimum time is 3. Step 2. Since the minimum time is on the last server, schedule A in the last available position. Step 3. Eliminate the job and go to step 1. But since we have only 1 position left and 1 job left, then we place that job in that position, and there's our Johnson's Rule schedule. And this schedule will minimize our total processing time. But when step 1 results in only 1 answer, then the Johnson's Rule will be unique. And this video only considers unique schedules from a Johnson's Rule. Now we can see the concept of Johnson's Rule. 1. Schedule jobs with the smaller times on the first server early in the schedule. Number 2. Schedule jobs with smaller times on the second server late in the schedule. Now let's see how these 2 concepts can be used to solve a Johnson's Rule problem with Excel. So let's bring in Excel. I've typed in a scheduling problem where we have the number of the job ID, time on the first server, and time on the second server. Now the concept has the jobs with the smaller times on the first server early in the schedule, and jobs with smaller times on the second server late in the schedule. So we need to identify which jobs are early and which jobs are late. So we have an if statement. If the first time is less than the second time, then we will designate that job as early. Otherwise, it's late. And so if we bring this down, we notice that some jobs are early and some jobs are late. And so we carry that down all the way to the job 40. So there's a designation of early and late. So now, let's highlight the job, the times, and the early and late designation, all 40. And then let's come up here to the Data tab, and let's sort it. Since my data has headers, I'll check my data has headers. And now I want to sort, first of all, on the early and late. I want to go from A to Z, because E comes before L, and so I will sort the early ones first and the late ones second. But then I want to add a level. Once I sort early and late, then I want to sort on time 1. So I click time 1, and this time I want smallest to largest because I want the smaller times first. I say OK, and now I have all the early times, and the minimum time on the first server goes all the way until we get to the late. Now when we hit the late times, we don't want that to go from small to big. We want it to go the other way because we want the shorter times on the second server at the bottom here, which implies that the larger times are in the middle. So we go back to our data, go back to our sort, but this time our data does not have headers, so I unclick it. So now we want to sort on column D. Column D is the second time, but this time we want to sort it largest to smallest because the time on the second server should start large and then end as the smallest. So now I click OK, and now this right here is the Johnson's Rule schedule. And that's how you solve Johnson's Rule schedules with Excel. Now let's look at the Gantt chart. A Gantt chart is a time plot of a schedule. So let's plot the schedule ABCD on the Gantt chart. So the schedule ABCD will be processed on server 1 and server 2 in series, where the processing times for server 1 is listed here, the processing time for server 2 is here, for ABCD in that order. So let's start with job A. A spends 4 days on server 1. Let me represent a day on server 1 with the number 1. So I have 4 ones. Then A proceeds to server 2 for 3 days. And let me represent a day on server 2 with the number 2. So I have 3 2s. Job B spends 2 days on server 1. But it has to wait for A to be finished on server 1 before server 1 can process B. Then it can process B for 2 days. Then it moves to the second server for 6 days. But it has to wait for the second server to be available before it can process 2. Then it can process 2 for 6 days. Job C spends 4 days on server 1. But again, it has to wait for server 1 to finish with A and B before it can process C. Then it can process C for 4 days. Then C moves to the second server for 1 day, but it has to wait for the second server to be available. And then once it's available, then it can process C for 1 day. Job D spends 5 days on server 1, but again it has to wait for 1 to finish A, B, and C. Then it can process D for 5 days. Then it moves to the second server for 4 days, but there is no wait time because the server 2 was finished a day ago. D can be processed for 4 days. And so there's the Gantt chart. But there's a lot of information we can gain from the Gantt chart. So let's look at the Gantt chart diagnostic. There's a number of diagnostics we can gain from the Gantt chart about the schedule, the jobs, and the servers. Let's start with the schedule. The time of completion can be pulled off the Gantt chart, or the total time of the project. It's very difficult to know how long this project's going to take in this order with just the times. But the Gantt chart, you can read it off very easily. Next is flow time. Flow time is defined as the number of days a job is in the queue and the servers, or the number of days a job is in the system before it leaves the system. For job A, it's 7 days. After 7 days, it leaves the system. For job B, we can see that it's 13 days. For job C, it's 14 days. And job D, it's going to be 19 days. And the flow of the last job in a schedule is always the time of completion of the project. The queue time. That's how long a job waits in a queue in front of the first server and in a queue in front of the second server. The queue time of the first job is always 0 in a schedule. For job B here, it waits 4 days in a queue in front of the first server, 1 day in a queue in front of the second server, so the total queue time then is 5. For job C, it waits 6 days in front of the first server and 3 days in front of the second server. So the total queue time then is 9. And for job D, it rates a total of 10 days in front of the first server. But in front of the second server, there's 0 queue time. So the total queue time is 10. Next is processing time. The processing time is the sum of the processing times on server 1 and server 2. 4 plus 3 is 7. B, 2 plus 6 is 8. C is 5. D is 9. But the flow time of each job is equal to the queue time plus the processing time, a property that will be useful in Excel. Next is server idle time. Consider time periods 14, 15, and 16. A server can only service one job at a time. But time period 14, server 1 and server 2 are both busy servicing one job. But in time period 15, 1 is busy, but 2 is idle. In time period 16, 2 is busy, but 1 is idle. So to calculate the server idle time in this type of queuing system will be a little different for server 1 than for server 2. So let's start with server 1. Server 1 will have no idle time from the beginning all the way to the end of the last job. But the time of the last job that is finished to the time of completion of the project, that will be the idle time for server 1. Now for server 2, we'll always have idle time at the beginning until it starts processing. It'll never have idle time at the end, but somewhere between the first job and the last job, we have to compare to see how many days server 2 will be idle. So we have 4 plus 1 is 5. But this merely describes the diagnostics in the Gantt chart. Let's see how to calculate the values in the Gantt chart and the diagnostics using Excel. I will use the relationships in this simple Gantt chart to illustrate how to develop an Excel solution for a larger scheduling problem. So let's bring in Excel. I've typed in the header information, and we're using the same scheduling problem we did for the Johnson's rule, where the number of jobs was 40. So let's start. The start time on server 1 of the first job in any schedule is always 0. The finish time is always equal to the start time plus the processing time. Now the start time for the second job is always equal to the finish of the server 1 on the previous job. So this is always equal to the one before. And the finish time is always equal to the start time plus the processing time. And now I can copy that down. I'll just copy it to here. I'll copy it further down later. Now the start of the second server would be the finish of the first server for the first job. The finish on server 2 is always equal to the start plus the processing time. But then the start of server 2 for the second job will be the maximum of the finish of server 1 on the current job and the finish of server 2 on the previous job. So this will equal the max of the finish of server 1 on the current job and the finish of server 2 on the previous job. And then the finish equals the start time plus the processing time. And now I can copy that down. I'll just copy it to there. I'll finish it later. Now the queue time. Well, the queue time on the first job in any schedule is always 0. On server 1, server 2, and the total. The queue time for the first server on the second job is always equal to the finish time of the previous job. So that's always going to be equal to the finish of the previous job. So the queue time in front of server 2 will depend on the finish of server 1 on the current job and the finish of server 2 on the previous job. And that number minus that number, the difference would be the queue time. So this would be an if statement. If the finish on the server 2 on the previous job is greater than the finish of server 1 on the current job, then that number minus that number will be the queue time. Otherwise, it's 0. And then we can add these two together. and there's our total queue time. And I can just copy these down now, and I'll finish that later. Now finally, the idle time. Well, the idle time for the job for server 2, if you recall, at the very beginning, it'll always equal the processing time on the first server on the first job. So that's always going to equal the first processing time. But then after that, when the finish time on server 1 on the current job is greater than the finish time on server 2 of the previous job, that difference will be idle time. So I have an if statement. When this finish is greater than the finish of server 2 on the previous job, then that difference will be idle time. Otherwise, it's 0. And then I can copy that down. So now that we have all the columns calculated, let's copy this down for the entire problem. All 40 jobs. And there we go. I've copied the titles down here so we can see the total, and the finish of server 2 on the last job in the schedule will be the time of completion. Also, the difference between the finish of server 2 and the finish of server 1 for the last job, that difference is the idle time for the first server. So let's go back up here, and so the time of completion is going to equal the finish on server 2. And then the idle time of server 1, let's go back down, will equal the finish of server 2 minus the finish of server 1, both for the last job in the schedule. So there we've completed the Gantt chart and the diagnostics on Excel. But we know that Johnson's rule will minimize the processing time. So the time for this particular schedule is 1910. Well, let's copy this over here, and let's see what happens with Johnson's rule. So right here, let me add a column, and that's going to be the early and the late, where we have if this time is less than this time, then I'll designate that as early, otherwise it'll be late. And so we're setting this up for Johnson's rule. So now we come back up here, we take the job, the time on the first server, second server, and early late designation. Now we go to data, and we go to sort. Now we have headers, my data has headers, and so the first thing we sort on is the early late, and that's A to Z. We add a level. Now we're going to sort on time 1 from smallest to largest, and that's the first half. Now we come down where the early changes to late right here, and I start with my late. I take my time 1 and time 2 along with the job ID, and here I go to my data, sort, but this time my data does not have headers, and I want to sort on column D to where I have largest to smallest, and there's my Johnson's rule schedule. And we can see that the time of completion is 1835 for the Johnson's rule schedule compared to the 1910 of the original FIFO schedule. And that's how much we can reduce the time using Johnson's rule. This is how to solve a scheduling problem with Johnson's rule for a queuing system with 2 servers in series. However, even though you may not have the same type of queuing system and Johnson's rule does not apply, the Johnson's rule concept can still be used to obtain a schedule that may not be optimal, but will be very good. So, the Johnson's rule concept can be used to develop heuristic procedures in Excel that can provide effective solutions in more complex systems. So this ends the scheduling video, Johnson's rule, and Gantt chart with Excel. I hope this helps. Thanks for watching.